start our learning of GCD and LCM, it's best to think of an example. So I'm going to write two numbers down, so 45 and 60. On the side, if you guys want, pause the video for an exercise on making the prime factorizations of the numbers. But I'm just going to write them down for us. So for 45, the prime factorization is going to be 3 squared times 5. And then for 60, it's going to be 2 squared times 3 times 5. So now, let's think about what GCD and LCM mean. So GCD stands for the Greatest Common Divisor, and LCM stands for the Least Common Multiple. So pretty much GCD is saying what's the biggest number which can divide both 45 and 60 evenly. So, and then for LCM, that's saying what's the least number which 45 and 60 both divide evenly. So let's think about GCD first. So by checking the factors of 45 and 60, where one can just write out their factor trees, so I'll just do that for us. So 1, 45, 3, 15, 5, 9, and then 60 would be 160, 230, 320, 415, 512, and 610. So pretty much we're trying to look through and see what's the biggest factor which is shared by both numbers. So you can see common factors like 1 are there, but obviously they're not the greatest. 3 is there, 5 is there, 9 isn't there, 15 is there, and 45 is not there. So by just doing a check, you can see that 15 is the biggest number, which both divides 45 evenly. So that's like 3, remainder 0, and 60 evenly. So pretty much, the GCD is equal to 15. So we normally write that as GCD of 45, 60 is equal to 15. Sometimes people use the notation as just the brackets, but this really depends on the context, since you don't want to get confused thinking that this might be a coordinate point. So normally just write this notation down. The least common multiple is the smallest one which both 45 and 60 divide evenly into. So what one might do is just check different multiples of one of the numbers, like 45, then 90, then 135, then 180. So multiples are pretty much just something which the number divides into. So 45 divides into 45, 90 is evenly divisible by 45. So pretty much, now that you list out some multiples, we can check if 60 divides into them. So 60 doesn't divide there, 60 doesn't divide evenly into that, nor does it divide here, but it does divide into this. So pretty much, from here, we can tell that 180 is the least number, which 45 evenly divides into, and also 60 divides evenly into. So we can write LCM of 45 and 60 is equal to 180. Again, a separate notation is using square brackets for it, but really, let's just write it out like that on above. Do not get confused. Now you might be asking, wow, isn't this a lot of trial and error to write down all the factors and even check all the multiples? Well, fortunately, using our knowledge of prime factorization, there's actually a better way to do this. So what I'm going to do is I'm going to write out the prime factorization, but instead I'll include all the primes. So 2 to the 0, so that's just 1. Any number to the power of 0 is 1. 3 squared times 5. And then we'll have 60 down here. So that's 2 squared times 3 times 5. So now, let's see what the GCD means. So pretty much, if my GCD number, so let's write that here, we have to decide what powers of primes it will have, since we discussed that every number can break into these. So if our GCD has like 2 to the power of 2, then are you sure it can evenly divide into 45, given that 45 has 0 powers of 2? So pretty much, with the greatest common divisor, you want to take the smaller one. Let's think. If we have to use 0 here, because it has to divide both of them. But if it has more than 0, then it won't be able to divide the top one, since who's going to supply the factors of 2? So pretty much, we just take the smaller one. So even here, think about it. We would take 1 instead of 2, because if we had 2 powers of 3, then how will we divide into 60? So we have that. And then here, we can see that they're both tied at 1, so we can just take 1 so they can both divide. And then computing that, you get 1 times 3 times 5, which is indeed equal to 15, as we saw before. Oops, sorry, not there. 15 as we saw before. Now, let's think about what the LCM means. So let's do the LCM number. So pretty much, in this case, we're still trying to assign the prime powers. Where then, from here, we're thinking, okay, if we want both of these numbers to divide into the bigger one, we should be taking the bigger power of the 2. Since if we take 2 to the 0 as in our LCM, then how's 2 squared going to divide into it, since they don't have any factors of 2? Like, just think about it as like a shop, where you have some factors of each number, and you want to make sure you're able to give that many factors when dividing. So we're taking the bigger ones in this case. So we take 2 squared, then here you would want to take 3 squared, because it's the bigger one. And over here, since they're the same, you just take one of them. So now multiplying this out, you get 4 times 9 times 5, which ultimately evaluates to 180, just like we had before. So this is a pretty nice property with prime factorization, where if you prime factorize two numbers, then you take the greatest common divisor by just taking the smaller one, and you can find the LCM by taking the bigger exponent. So this really shows how powerful the prime factorization is. Now before we end the video, there's one nice property I'd like to discuss. Given two numbers, a and b, you can say a times b is equal to the GCD of ab times the LCM of ab. So that's might be interesting, how does that work? Well, let's think about it. For each of our numbers, so let's just say a is equal to 2 times 3 times 5 to a1, a2, a3, just 3 variables, and b is equal to 2 to the b1 times 3 to the b2 times 5 to the b3. Pretty much what the GCD is saying is we're going to take the smaller one of a and b, smaller a1 or b1. Then we're taking the smaller a2, b2. We're taking the smaller a3, b3. We're taking the smaller one essentially. So there's either only one smaller one or one bigger one. So when we actually multiply the two numbers out, so a times b, we pretty much have 2 to the a1 plus b1, because exponents add, 3 to the a2 plus b2, and 5 to the a3 plus b3. In our GCD, so I'll just start GCD number, we might have, let's just say, a1 is smaller than b1, a2 is smaller than b2, a3 is smaller than b3. In our GCD, we're taking the smaller one, so we'll have 2 to the a1, then 3 to the a2, and 5 to the a3. And in our LCM, we're taking the bigger one, so we'll have 2 to the b1, 3 to the b2, and 5 to the b3. And then when we multiply the numbers out, they add, and they get the exact same thing as ab. The interesting thing is that if I change the sign, let's say I said a2 is bigger than b2, then that doesn't really change this property at all, since what would happen is our GCD would just have the smaller one, which is b2, and our LCM will just have a2 as the exponent. but they still add together since it's addition, so it doesn't matter which order you add. So from this video, we understood how to calculate the GCD and LCM by first understanding what they were through pretty concrete examples, where we discussed how to do the guess and check method, and also how we can use prime factorization to figure out nice relationships such as this one, and also how to calculate them more concretely. So as a last problem for this video, please calculate the GCD and LCM of 18 and 24. Pause the video and we will discuss. Alright, now that you're back, let's discuss how we can find them. So first, we can do the guess and check method, and then we'll do the prime factorization method. So for 18, we have 1, 18, 2, 9, 3, 6. And for 24, we have 1, 24, 2, 12, 3, 8, and 4, 6. So now let's see which ones are common and which is the bigger one. So 1 is common, 2 is common, 3 is common, 4 unfortunately isn't common, 6 is common, and that seems to be it. So since the biggest one, which is common, is 6, then we know the GCD of 18 and 24 is equal to 6. Now let's try to do the LCM. So we're going to list out the multiples of 18. So let's write them: 18, 36, 54, then you have 72, then you have 90. So now let's check if 24 divides into each of them. So 18 divided by 24 doesn't work. 36 divided by 24 also doesn't work, unfortunately. 54 divided by 24 doesn't work. But 72 divided by 24 is equal to 3, and that works. So from this, you can see the LCM is equal to of 18 and 24 is equal to 72. Now let's try using our prime factorization method. So we're going to do 18. If you guys want to pause the video and try the prime factorization, you are welcome to do so. But 18 is equal to 2 squared times 3 squared. Then 24 is equal to 2 cubed times 3. So now let's think. GCD number. We want to take 2 to some power and 3 to some power. So for 2, we can take the smaller one. So 2 and 3, we take 2, since we're trying to find the one which fits into both. And then, sorry about that. 18 is not 2 squared times 3 squared, it's actually just 2 to the 1 times 3 squared. So we take the smaller one. So it's going to be 2 to the 1. Then for 3, we take the smaller one again. So that's going to be 3 to the 1. So then we get the GCD is 6. Although there's nothing stopping us from doing the same method for LCM, where we choose the bigger one, let's try applying our property we learned earlier, where if you have AB, that's equal to the GCD of AB times the LCM of AB. So A times B, 18 times 24, is equal to 6, which is this, times LCM of AB. Although this is an algebra trick, which is in solving single variable equations, which we'll be talking about in our next set of videos, what you would do is you would just divide by 6 on both sides, and then you would end up getting an answer of LCM of AB is equal to 72. We can use our traditional method with the maximums to even confirm this, where you have the bigger one being 3 here, so 3, and the bigger one being 2 here. So then you would get 8 times 9, which is 72. I know that was a lot, but I hope you guys learned how useful the prime factorization is in the case of GCD and LCM and learned an interesting property. I hope to see you in our next videos. We're going to be learning more algebra. Thank you so much for listening.